On this slide, we have a few of the interfaces and classes from the collections framework. Notice it's displayed in a hierarchy. We have a parent-child relationship based on the interfaces and classes which inherit from other interfaces. This is not a comprehensive look at the collections framework, only a few of the interfaces and classes we can find there. If you look at the legend, each interface is displayed in a white box with a red outline. A class is displayed in a green oval with a white outline. Based on the graphic, you can see that some interfaces extend other interfaces. This means that the interface inherits the methods of the parent interface. For example, the list interface extends the collections interface. The list interface will inherit the methods of the collections interface. You'll notice that classes can also inherit from interfaces. For example, the array list and linked list inherit from the list interface. Keep in mind that when we are working with interfaces, we must use an implementing class for calling the methods in our code. This is why when we declare the list interface, we must instantiate it with the new keyword and use an implementing class like ArrayList or linked list. In this video, we will use the priority queue and hash set to implement methods from the collections interface. In addition to the collections interface, there is also another useful interface called the map interface. We will be implementing the map interface using the hash map implementing class. Let's take a closer look at the interfaces and classes found in the collections framework. Let's start our discussion by looking at the queue interface and using the priority queue to implement this interface. A queue is a collection that represents a waiting line. Just like the waiting line at a grocery store or a bank, where people go to the back of the line and wait their turn to be serviced. Elements in a queue are inserted at the back and deletions are made from the front. One implementation of the queue is the priority queue. The priority queue implements the queue interface, and insertions are made in sorted order determined by a comparator. Realize that this is not a strict first in, first out ordering. A sorting will take place, and the smallest value will be placed at the front of the queue to be removed first. Some important methods that you will find with a priority queue include the offer method. This inserts a specified element into the queue and returns a Boolean value based on the success or failure of the insertion. There is a similar method called add, but it throws an exception on failure rather than returning a Boolean value of false. The peek method returns the head of the queue or a null if it is empty, and it does not remove the head. A similar method to the peek is called element, but it throws an exception instead of returning a null value when it is empty. The poll method removes the head of the queue and returns it. Poll will return null if the queue is empty. The remove method is similar to poll, but it will throw an exception instead of returning null when the queue is empty. Let's take a look at working with queues, and in particular the priority queue, by performing a code review. You'll notice that I've opened the Chapter 16 project in NetBeans and navigated to the priority queue test file. On line 1, you can see we've declared the package, which is QPack, as indicated in the projects list. On line 5, I've imported the priority queue. Line 7 declares the class, and line 9 declares the main method. On line 12, we're declaring a priority queue as a double and instantiating that priority queue as a new priority queue. One of the things that we can do with a queue is we can specify the size. For example, if I wanted 11 elements in this queue, I could simply type the number 11 as an argument, and this integer will be passed into the constructor of the priority queue. It's also worth noting that line 14 provides us with an excellent example of a type wrapper class. Notice the word double appears as the data type for this queue. We know that it's double as a class because we're using the capital letter D here. If we used a primitive type, you'll notice that we get an error. Remember that data structures can only work with objects. So here we have to declare a class name, not the name of a primitive type. This is a common error that people who are new to working with data structures will make. Notice if you mouse over the error, it indicates that a reference is required. This means we're looking for a class, not a primitive type. I can change the double back to a capital D to clear the error. On line 17, 18, and 19, you'll notice that we are inserting elements into our queue. First, we insert the double value 3.2, then we insert the value 9.8, then we insert the value 5.4. Realize on line 18, 9.8 comes after 3.2 numerically, so 9.8 will go to the back of the line. On line 19, when we use the offer method, 5.4 will be inserted in its priority location. This means it will appear after 3.2 in the queue, but before 9.8. After performing the offers, we'll simply print the queue. This will happen with a header on line 21 and the while statement that runs from line 24 to 28. Notice on line 26, we're using the peek method to view the top element or first element in the queue. True to our type wrapper, notice that we are able to take the object from the queue and print it as a float as if it were a primitive type. After printing the element, we are going to use the poll method to remove the head or top element from the queue. This is the end of this method. Let's run the code. And you'll notice that the elements were added in ascending order. We finished looking at queues. Now let's take a look at the set interface and how it is implemented using the hash set implementing class. A set is a collection that has unique elements. There are no duplicate elements found in a set. Classes which implement the set are the hash set. The hash set stores elements in an unsorted order in a hash table. Because the elements are unsorted, it is very efficient to insert new elements into a hash set. Searching for elements in a hash set, however, is very inefficient. Another class which implements the set is the tree set. With the tree set, elements are stored in sorted order in a tree. As you might have guessed, inserting elements is not as efficient as with the hash set because elements must be inserted in a sorted order. However, retrieval using a tree set is much more efficient than using the hash set. Important methods of the tree set include the head set, which gets a subset of the tree set in which every element is less than the specified value. The tail set, which gets a subset of the tree set in which every element is greater than or equal to a specified value. The first method gets the smallest element of the set, and the last method gets the largest element of the set. Let's take a look at some code to see how the hash set is used. You'll notice I've navigated to the setpack package and opened the set-test Java file. To the right, we can see the code, and on line 1, we've declared our package setpack. On lines 5 through 9, we have various import statements. Notice we are importing the hash set class on line 7 and the set interface on line 8. We've also imported the collection interface and the list interface. A particularly interesting class that we've added on line 6 is the arrays class. Like we've seen with collections, files, and paths, arrays will provide us with a class that contains a variety of static methods that we can use for working with arrays. In particular, we are going to be using the arrays class to convert an array to a list. Moving down to line 11, you'll notice we've declared the class, and line 13, we've declared the main method. On line 16, we have an array of strings called colors again. You'll notice that the colors array contains a variety of different colors. We want to convert this array quickly to a list. We can use the arrays class mentioned on line 6 and the asList method to convert the colors array to a list and assign this value to a list. On line 19, we are printing the list. If we want to print non-duplicate values, we can call the method print non-duplicates, which appears in this class. You'll notice print non-duplicates passes the list as an argument. If I go to print non-duplicates, you'll notice the list is passed in as a collection. This is permitted because a list is a type of collection. We can pass in the list as a collection, and notice we've changed the name of the list to values. If we look at our collections framework, we've declared a list, passed it into our method as a collection, and now we're implementing the collection as a hash set. We've already seen that we passed it in as a collection in line 26. Here you can see we are declaring it as a hash set on line 29. We've declared a set of strings and implemented that set of strings as a new hash set. Notice the constructor for hash sets can accept a collection as an argument. Because a set does not allow duplicate values, we can now print the non-duplicate values. Notice on line 31, we have a heading, non-duplicates are, and then a for loop to print each of the values that's stored in the set. Line 36 simply prints a line feed at the end of the line. If we return back to the top, if we run our code, you can see that first the list prints based on the print statement at line 19. Next, the non-duplicates print based on calling the print non-duplicates method on line 22. Notice any duplicates like white, orange, and gray only appear one time in the non-duplicate values. Lastly, let's take a look at the map interface. You'll notice that map does not directly inherit from the collections interface, but map is an interface which provides us with valuable functionality as programmers. We can use the hash map class as an implementation of the map interface. A map associates unique keys to values. Realize that there are two parts to the map, the key and the value. A map can have two different types of relationships between keys and values. There can be a one-to-one relationship where the map contains unique keys and unique values. There can also be a many-to-one relationship where the map contains only unique keys and the values may be duplicated. Realize that maps differ from sets. Sets only contain values, where maps contain both a key-value pair. Classes which implement the maps are the hash map, where elements are stored in a hash table, and a tree map, where elements are stored in a tree. Let's take a look at a map in a code review using the file wordtypecount.java. You'll notice that I've opened wordtypecount.java in NetBeans. As we saw in previous examples, the first line declares the package, lines 5 through 9 perform various import statements, line 11 declares a class, and line 13 declares the main method. In line 16, we are declaring a map and instantiating it as a new hash map. You'll notice that the map has two parts. The first class that's listed represents the key. In this case, we're using a string to store key values. The second class referenced in the map is the value. In this example, we're using an integer to store values. In this program, we will ask the user for input and count the number of times each word appears in the information that the user gives us. In line 18, we're calling a method called createMap and passing the map that we created in line 16. If we navigate to createMap, you can see that the map is passed as an argument. Then on line 25, we are instantiating a scanner. We ask the user to give us some information using a print line statement, and then we scan the entire line of input from the user using the scanner next line method. We will store the information from the user in a string called input. After this, on line 30, we will create an array of strings and name this array tokens. The tokens array will contain an array of words typed by the user. Notice the input calls the split method and splits the string anywhere there is a space. This will put each word of input from the user in a separate element in our tokens array. After creating the array, we have a for loop. We are creating a string called token, and for each token in the tokens array, we are converting that token to a lowercase word. After the conversion, we will store the value in a string called word. Next, we perform a conditional statement with the map. We will check the map to determine if it contains the word that we are sending it. If the word is in the map, we will perform the if part of the statement. We will create an integer called count, which will store the value from the map. Map.getWord goes to the key which matches our word and gets the value. This value is stored in count. Next, we will call the put method and put the value of the count plus 1 in the value of that word. If the map does not contain the word from the user, we will call the put method and store the word as the key and a value of 1. After creating the map, we will call a method called displayMap, which will also pass the map as an argument. If we display my map, you can see the map parameter appears in the parameter list. The first thing that we are going to do in line 51 is we are going to create a set. This set will be generated by calling the keySet method of map. This will take all of the keys and store them in a set called keys. Remember, these keys are simply the words that the user has typed in. Next, on line 54, we want to sort the keys. To do this, we declare a tree set named sorted keys. We will instantiate the tree set by passing in the keys set to the constructor of the tree set. This will simply store the words that the user typed in sorted order. On line 56, we're going to print a header, and on line 59 and 60, we are going to print the keys and the values from our map. Notice we are creating a string called key to navigate through each word in the sorted keys set. In line 60, we are calling the get method of the map and passing in a key to get the value stored in that key. This is basically the count of how many times a word appeared. We are also printing the key itself. So first the key will print, which is a word. Then the value will print, which is our integer. Lastly, on line 62 and 63, we are printing the size of the map and whether the map is empty. If we run our code, enter a string, you'll notice the words from the user input have been tokenized, and the displayed map method displays each one of the words on a separate line. The values correspond to the number of times each word appears in the user's input. You'll notice that the keys appear in alphabetical order because of the tree set that we created. This places the words in an alphabetized set. We navigated through each word in the set, retrieved the word from the map, and displayed the word and the number of times the word appeared. At the bottom, you can see the size of the map and whether the map is empty. This concludes our discussion of queues, sets, and maps in the collections framework. I hope you found this information useful. Please ask if you have any questions.